In this video, we're going to explore the use of an analytical technique known as titration. In some cases, some solutions cannot be accurately made by the weight and dilution methods that we've discussed before. This is especially true if the solute that we are using is either impure or unstable in some way. When this is the case, what we can do is make up a solution of an approximate concentration using the mass, and then we standardize the solution against a known standard. The standard compound is one that is incredibly stable with a known molar mass and has at least 4 or more significant figures in that molar mass. This allows us to be very exact. In order to standardize a solution, we perform what we call a titration, where a measured volume of the solution is added to a known amount of the standard. Since the standard is something that's very stable, we can find its precise amount very easily. We use an indicator which tells us when we have added enough moles of the standard to precisely equal the moles of solute that were initially present. This endpoint tells us when we are done with the titration. We can then calculate the concentration of the solution, and we'll show some examples of how to do that. A titration depends on many of the solution stoichiometry concepts that we've already discussed. We must first write and balance the equation for whatever reaction we are using, and then we see that moles of one thing in the reaction will be converted to moles of another thing, and then we can solve the problem for whatever we're looking for. The endpoint is usually some sort of visual signal. In the case of acid-base titrations, we use an indicator known as phenolphthalein, which is colorless in acidic solutions and pink in basic solutions. These would be the steps if, for instance, we were going to titrate an acid with a base, which is a fairly common titration technique. We use an analytical instrument known as a burette, which is a measuring device usually calibrated in divisions of 1/10 of a milliliter. And so since it's calibrated in divisions of 1/10, we can actually read them to 1/100th of a milliliter. So they are fairly accurate measuring devices. We fill our burette with a base of a known concentration. We then add some acid down into an Erlenmeyer flask, which might be an acid that we don't know the concentration of. We want to find the concentration of this acid. And so we slowly add base from our burette into the flask until we reach our pink endpoint in the reaction. At that pink endpoint, we have added precisely enough base from the burette to react with all the moles of acid initially present. And so at that endpoint, our moles of base added is equal to our moles of acid initially present. And so when you're physically in the lab carrying out this process, you start by adding solution into the burette. Typically you would want to use a funnel because the burette openings are fairly small. And then we would add our solution from the burette into our sample of acid, and then the reagent, in this case the base, would react with the acid that's in the flask. An indicator shows when the exact stoichiometric reaction has occurred. And if you recall that if it's an acid-base reaction, our net ionic equation looks like this. And so at the equivalence point, when an exact stoichiometric reaction has occurred, we have added exactly enough OH- to be equal to the moles of H3O+ that were initially present. This would be for an acid-base titration, but the basic concepts would remain the same for most types of titrations that you would do. At that endpoint, you would have an exact stoichiometric ratio. You would just use different indicators for different types of reactions to show you when that has been reached. So we've looked at graphics like this before. In this case, in the titration, we would have a volume of one of the solutions, which we would then be able to relate to the moles of that solution present, which we can then relate through the balanced chemical equation to the moles of another solution, which would then relate again through the molarity to the volume of that solution. In this example, we're going to look at a classic acid-base titration. Our first step is to look at our balanced chemical equation. So in this case, we have our hydrochloric acid plus our sodium hydroxide will react to give us sodium chloride and water. The most important part here for us to note, and we will use this later, is that it is a 1-to-1 stoichiometric ratio between our hydrochloric acid and our sodium hydroxide. So in this example, we want to know what volume of 0.600 molar HCl we will need in order to neutralize 25.0 milliliters of 0.175 molar NaOH. And so we can start with the information that we know, which is our 25.0 milliliters of NaOH. We know that we're going to need that in liters because we'll be using molarity. And so we convert to liters. And then we're going to want to convert over to moles of NaOH using our molarity. Next, we can use our stoichiometric ratio of 1-to-1 HCl to NaOH to convert over to moles of HCl. And now we use our molarity of HCl to convert over to liters of HCl. And finally, it's probably going to be convenient for us to think again in terms of milliliters. And so we'll convert back to milliliters. And so once again, as in any stoichiometric calculation, when you're using dimensional analysis, let's take a look at how our units cancel out. Our milliliters cancels out of NaOH, liters cancels out, moles of NaOH cancel out, moles of HCl cancel out, our liters of HCl cancel out, and we'll be left with milliliters of HCl. And so we perform the calculation, and we find that 7.29 milliliters of our 0.600 molar HCl solution will be necessary in order to neutralize 25 milliliters of 0.175 molar NaOH. The standardization of an NaOH solution is a fairly common tool that's used in labs. Sodium hydroxide is what we term hydrophilic, which means that it is water-loving. This results in solid NaOH having an unknown amount of atmospheric water becoming attached to it. And since we don't know how much water might be attached to it, this makes it impossible for us to create a solution of a precisely known concentration from solid sodium hydroxide. We can come close, but we don't know what the exact concentration is because we don't know how much of the mass that we have weighed out is a result of that attached water. And so we can use something called potassium hydrogen phthalate, KHP, which is a primary standard. This is a primary standard that we can know the exact mass of very, very accurately. And it's used to standardize NaOH solutions and reacts with NaOH in a 1-to-1 ratio. After standardizing NaOH with a solution of KHP, that sodium hydroxide can then be used as what we call a secondary standard in order to find the concentration of acids. This is how a sample of hydrochloric acid would be standardized, for instance. You would first standardize an NaOH solution against the primary standard KHP, and then you would go through the same process to standardize the HCl against that NaOH. In order to perform a standardization of sodium hydroxide, we dissolve a precisely known amount of KHP in water into an Erlenmeyer flask. We have the base, the NaOH, that we're trying to find the concentration of in our burette, and we slowly add that to our KHP until we reach our pink phenolphthalein endpoint. Remember, at the endpoint of a titration, the moles of each reactant will be equal to each other. And so thus in this reaction, at our endpoint, the moles of NaOH are going to be equal to our moles of KHP. We can use this to then perform our calculations. And so, in this example, we're trying to find our precise concentration of NaOH, and in our titration, we needed to use 14.6 milliliters of our NaOH solution in order to get to our endpoint of a solution that was prepared with 0.374 grams of KHP into our Erlenmeyer flask. Now once again, remember the key to a titration is at that endpoint, our moles of NaOH are going to be equal to our moles of KHP. So the first thing that we want to do is calculate how many moles of KHP were initially present in our flask. And we can simply do that using our molar mass of KHP. And we know that KHP and sodium hydroxide react together in a 1-to-1 molar ratio. And so this tells us that at the end point of this titration, we have added 0.00183 moles of NaOH. Now let's just think about where we're at. This means that there were 0.00183 moles of KHP down in our initial flask, and since it's a 1-to-1 ratio at the end point, we had to have added 0.00183 moles of NaOH from our burette. We also know, though, that in that 0.00183 moles, that came from 14.6 milliliters of NaOH. And so, we can easily convert that to molarity by taking our 14.6 milliliters, converting that to liters, and now dividing our moles of NaOH by the amount of liters that we used for a final calculated molarity of 0.125 molar NaOH. And so this was simply an example of how we can use titration in order to find the concentration of an unknown solution, as long as we have something like KHP or some other standard to base that on. Titrations in general are a very powerful analytical tool and are used in a wide variety of chemistry applications. The basics of all titrations, however, remain the same, in that at the end point, the moles of one thing added will be equal to the moles of what you had initially present. I hope this video was helpful. If you're looking for more help, please be sure to visit the website.